Okay, let's have a look at this example. So note pivot here and the pivot here. So now the pivot is not at the end. So if we decide that the pivot is going to be at B, for example, then this force is going to be trying to turn it around clockwise. To determine whether or not it's anti-clockwise or clockwise, think what will happen to this beam if that's the only force that acted. Well, it would go round clockwise, wouldn't it? So, and that's anti-clockwise, that's anti-clockwise, that's anti-clockwise, and the reaction force at A would be clockwise. So you've now got two clockwise moments. So a little bit more of a complex equation to solve, but I'll leave you to have a little play with it. It's the first thing to note about this. This is unusual. The second thing is this, which is bringing us to the idea of what do we do if we either take into account the mass of the whole beam, in which case one of these would go the full length of the beam, or we have the load spread out. This is the way that we show a load being spread over a certain distance along the beam, which could be part way along or all the way along. And it's called a uniformly distributed load, a UDL, a uniformly distributed load. And it's talked about in the notes, UDL. If you look at this, it's telling you how it's distributed. 1.5 kilonewtons per metre. So this thing is spread over a distance between 3 and 8 metres, so that's 5 metres between there and there. So this force is 5 metres long and it's 1.5 kilonewtons per metre. So 1.5 times 5, 7.5 kilonewtons. So this is a 7.5 kilonewton force, but distributed over 5 metres. How do we take account of that in a moment diagram? Well, what we do is we replace this whole force with a point force acting in the middle. And we replace that by a squiggly line, which means that it's not a point force, it's a UDL, but we're replacing that UDL with this of 7.5 metres. So what I do is I replace that with a force of 7.5 kilonewtons acting halfway along at this point. So what's halfway between 3 and 5? At 5 metres along there, so that'll be at 5.5 metres along the beam. So I replace the UDL with a point force, but I use a wiggly line to show that it's not a point force, it's a UDL. So now I can treat this UDL as a point force of 7.5 kilonewtons acting at either 5.5 metres from that pivot or whatever it is from that pivot there. So I'd have to work out that distance. And then I can use exactly the same formula as I did before, whichever convention you decide to use. When it comes to drawing the shear force diagram, I have to think again, and I'll leave you to think about what happens there. I've got a point force acting, so I'm going to start my shear force diagram with a reaction force acting up this way, and then it's going to continue in a straight line and then come down 8 kilonewtons, as we've done already, and then it's going to, nothing's going to happen between here and here, but what happens here? Think about that. And then what happens between here and here, and then we've got another point force acting and another point force acting, then the reaction force. So we're back in familiar territory here, and then we have the gain at the end here. It should come back to the x-axis if you've done it correctly. So your homework is to complete this question, find a reaction force at A, reaction force at B, use the up force and down force to check you've done it correctly, and then have a go at drawing the shear force diagram.